campus, and around a student strength of around 3,000. So, thank you. So out of which around 10% are PhD students. So we have a big component of PhD students in our institute. So it has the infrastructure that you would expect in any good institute. So because this is primarily a computer science based institute, we have departments that are all affiliated to computer science. So we have the traditional computer science engineering, but along with that we also have departments like computer science and design, computer science and mathematics, computer science and humanities, and computational biology. And along with that, the ECE, which is Electronics and Communications Engineering. So these are our academic departments and educational resources. So I belong to the Electronics and Communications Engineering department. So we are a very small department of around 26 faculty members. Like I said, our department was started in 2012. So our first undergraduate batch graduated in 2016. But our PhD program started right from the beginning, 2012. So our first PhD student graduated in 2017. So our department is around 12 to 13 years old, so quite young. So I'll switch gears a little bit, and I'll just describe what we had the last few days at IIIT Delhi. So we conducted the IEEE Signal Processing Society Seasonal School on synthetic aperture imaging for radar, sonar, and optics. So that was Tuesday, Wednesday, and Thursday, which is why I couldn't come here yesterday. So so we had a very exciting lineup of speakers who presented tutorials on radar, so different aspects of radar, and ISAC, sonar, and optics. So these were all mostly aimed at graduate students, doctoral students, young career professionals. So that was the objective of the summer school. So we had a poster session and we had a social visit to Humayun's tomb yesterday. So this summer school was technically sponsored by the Synthetic Aperture Technical Working Group of the IEEE Signal Processing Society. So we have Samuel here, who is the vice chair of the working group. And financially, it was sponsored by the Office of Naval Research, the IEEE Signal Processing Society, our department, and the AESS student branches. So big thanks to all our sponsors. And we successfully concluded the signal processing summer school yesterday. So switching to today, we have a really exciting lineup of speakers. So covering many different topics. We also have a poster session at 11:30. So our students are going to be presenting their recently published works in these posters. So we encourage all of you to interact with them and give them any feedback. So that would be great. So after lunch, we'll be having a panel discussion. So that will be very interesting. We'll have people sharing different perspectives on the opportunities and challenges of signal processing and machine learning. And in the evening, we'll be having a tutorial on cognitive radar. So this tutorial follows the initial tutorial presented at the summer school by Dr. Muralidhar Rangaswamy. So this is like the follow-up to the introductory session provided at the summer school. So with that, we can start the session, and we welcome our first speaker. Thank you.
I will let you find it for me.
Okay. So now, how do you make it full screen? Control.
Control L, yeah.
L.
You have to have a long hand.
Okay. Thanks.
I'm going to minimize this here. This part here. Right? There. All right, thank you very much. It's a pleasure to be here. This is my first time in India. I've been here a week and have really enjoyed my time here. So I've seen many different and interesting things, and it has certainly instilled a desire in me to come back because I know it's a big country and there's a lot of different things to see. And so anyway, thanks to Arpan, thanks to Vijay, thanks to all of you for organizing this workshop. And I'm going to talk a little bit today about connections of, I guess you'd call it machine learning and signal processing and wireless communications. This is a picture of our campus, by the way. It's also a very lush and green place, and of course you'd all be welcome to come. Does this work? Not quite. Okay, I'll try this. There we go. First, I want to acknowledge the participation of a number of collaborators that have worked with our research group on this particular topic, and it's a large list. But the key figures, of course, are the students and the postdocs who did most of the work. That would include Nan Nguyen from University of Oulu, my former PhD student Van Lee Nguyen, who just started a position at the University of Kansas, and then, of course, we have several others here that I'm sure their names you will recognize very well. And, of course, I'd like to acknowledge the National Science Foundation for supporting all of this work. So, as I mentioned, most of the work I've done in recent years has been connected with wireless communications, signal processing for wireless communications. And I've been a reluctant participant in the machine learning wave. I shouldn't say reluctant. Mostly it's just that I'm old and I'm used to my old ways. I've been working on standard model-based signal processing and model-based wireless communications for many years, and it's hard to teach an old dog new tricks. The picture up here, of course, is just an illustration of the classical communications structure, architecture of the communications transceivers, starting with bits on the left, going through coding, modulation, spatial coding, pre-coding, and then D to A, pulse shaping into the RF chain, through the channel, and then back again, each block kind of undoing at the receiver what was done to the signal at the transmitter so that hopefully the bits that come out are the same as the bits that went in. So this is the classical architecture, of course, that most communication transceivers have been designed under for decades now. It's well understood. It's served us well, I would say. And yeah, this has been the focus of research in wireless communications, these different blocks over many, many years. As I mentioned, based on well-established models, the expected performance of such a system, one of the reasons why, of course, it's been around so long is because we understand basically how the system performs. We know how the system basically will perform. We have bounds that have been set. We try and get close to those bounds, but more or less we know how such a system will perform once it's implemented, and this has been the foundation of nearly all communication standards, as I mentioned. On the other hand, I would say it's based on a reductionist kind of view, right? You break this problem down into little pieces and you solve each of those pieces, all of the problems associated with each of those pieces, more or less separately from the rest. So this limits flexibility to some extent. It leads to a relatively static design because there's not much room for, much elbow room within each of these little blocks to do something fancy. There is some limited flexibility. Of course, adaptive coding and modulation is implemented in the standards, among other things. But it's an architecture that emphasizes performance, I would say, over energy efficiency. That hasn't been the driving force until, of course, more recently. On the other hand, we now have the emergence of what people call 6G, which is still up for debate about what actually 6G will mean. There's been some discussion over the last few years about what 6G will include, what will make it different from 5G, and this notion of native IA, native machine learning, has been one of the key components that has been proposed for making 6G new and hopefully more capable. This is part of a little block diagram from Nokia Bell Labs website showing kind of, again, the standard communications architecture that we are using currently in 4G and 5G. And their proposal, or I would say their projection that advanced 5G, it says here, it will replace multiple processing blocks with those based on AI and ML. Okay, that's an interesting viewpoint, perhaps controversial. And they go further and say that in 6G, 6G AI and ML will design parts of the physical layer. And in fact, in this particular picture, it in fact shows the entire physical layer being replaced by an end-to-end neural network, which I think is maybe a little bit fanciful, but nonetheless, this is a topic of hot research. Where does AI ML fit in communication systems? I think it's easy to understand how machine learning can be applied at higher layers of a communication stack. The question of what can be done with AI ML at the physical layer, though, I think is a more interesting and difficult question, just due to the timescales involved at the physical layer and how rapidly things change. So, anyway, my point here is just to indicate that this is the hot topic right now. Is what's 6G going to be? And of course, the answer is, well, maybe AI ML will be part of that vision. And other than that, there's a lot of uncertainty, actually, about what 6G will turn out to be. So what does a native AI solution for 6G offer that maybe wouldn't be offered by a classical architecture? Well, there's potentially a lot more flexibility in such a system, especially if you try and do some kind of end-to-end design or combining blocks together and doing things jointly that you would otherwise do individually. You could target the custom application-specific designs with such a network. Perhaps one of the biggest draws of such a network architecture would be the fact that it can be implemented with relatively low cost. Once the network is trained, once you have some kind of machine learning algorithm running at the physical layer, supposing you can do that, it's a relatively simple matter to run the data through such a network, because it's just multiplies, adds. You start on one end of the network and out comes the answer on the other end. It says low-cost design here. I would say maybe. Of course, training is involved. We'll talk about that in a minute, but certainly from an implementation point of view, there's a lot of attraction to a solution that's based on a neural network type architecture. I would say the other potentially exciting development that such an architecture offers is its ability to enable what is called task-oriented or semantic designs for communication. So in a task-oriented or a semantic communication system, instead of treating the communication process from bits to bits as a bit pipe, you take into account the semantics of the information you're trying to send, and you encode semantics rather than bits. And at least conceptually, this has a lot of interesting promise and a lot of interesting, intriguing possibilities. And a lot of those, of course, are based on machine learning type algorithms. So it does mesh well with this type of vision of a physical layer designed with artificial intelligence and machine learning. So those are definitely pluses for this kind of approach. On the other hand, I mentioned that you have to train these networks, and that takes some time. That takes some assumptions about how the environment behaves once you put the network there. And it can be a fairly large overhead. These models can be sensitive to overfitting because there are a lot of parameters, and if the thing you're trying to implement or model is relatively simple and you've got a lot of parameters, well, this leads to overfitting and strange behaviors can result. The networks are sometimes hard to generalize in the sense that you train the network for one situation, one communication scenario or application. If you then deploy the network in an environment that's different, we don't know necessarily how the network will perform. And then I would say, finally here, because we have these decades of experience in designing communication systems, we know the modality of how this is done. It would be nice to incorporate some of the things we've learned from these decades of designing communication systems into a machine learning architecture. And sometimes, of course, black box models don't allow us to do that very well. Here's a cautionary example. I would say this is from a well-known article that it's cut off here, I'm sorry, by Emil Bjornsson and one of his students, showing what can happen if you kind of blindly go about applying a black box machine learning type approach to a very simple problem that can be solved with classical methods in an optimal way. So this is QPSK signal detection and Gaussian noise. You see the 4 clouds corresponding to the noisy received QPSK symbols. We know, of course, on the lower right, this is the optimal decision boundary definition for such a system. But what Emil and his group showed that is if you train a black box neural network to do this detection over several tens of thousands of observations of this channel, you get the very suboptimal architecture on the left. Now, this particular decision boundary choice might work particularly well for the training data that was used to generate it, but we know that in general this would be a suboptimal approach to doing so. So there's clearly room for improvement between black box approaches to AI and ML in communications and, of course, purely model-based approaches. So what do we need? What I think we need, at least to implement such algorithms at the physical layer, especially at the physical layer, we need solutions that are explainable at least to some degree. We have to know what this machine learning network is doing. They're generalizable. It should be able to work in different types of environments than the one it might be trained in. It should have a meaningful parameterization. The parameters that we're designing the network for, they should have some meaning rather than just weights and biases and so forth. We would like to incorporate the decades of domain knowledge that we have from communication systems. We would like them to have modest dimensionality and not require a lot of training, especially at the physical layer where we have to do this, where symbol rates are on the order of tens and hundreds of megahertz or beyond, and are not subject to the issues related to overfitting. So that brings us to the topic of today in my talk, and that is the one approach that I think is maybe an in-between step between the two worlds of the conventional and the new, is the idea of deep unfolding in wireless communications and signal processing in general. So deep unfolding is not a new topic, particularly. You can see there was some early work done in the early 2010s on the use of this idea, which I'll explain in a moment, for sparse coding, sparse signal processing. It wasn't called deep unfolding at that time. It had a different name. Of course, 2010 in the terms of machine learning, This is an ICML conference paper in 2010, which is, by now, of course, classical. That's only 15 years ago, but that's a long time ago in this field. And then the application of deep unfolding to wireless communications, I think, was first brought to bear in 2017 by Ami Wiesel and some of his students, where they applied the idea to MIMO detection, a simple application of MIMO detection. So it's been around. This particular application that Ami worked on was a fairly simple one, and probably under the assumptions that he used, it probably isn't really a problem that's well suited for machine learning, but it was more of an example of how you could use this technique of deep unfolding. So today I'd like to talk about maybe some examples that are a little more difficult to handle and for which a machine learning approach does provide some benefits. So the idea behind deep unfolding is at least for wireless communication system design, is the observation that when you're designing advanced transceiver algorithms for pre-coding, decoding, equalization, channel estimation, and so forth, they often boil down to fairly complicated iterative procedures. Either whether you're designing the system or whether you're actually implementing an algorithm to process data, many of the more advanced approaches require some kind of iterative approach, iterative algorithm, where you're taking a vector of data or parameters and updating it through this iterative process. ZL plus 1 equals some function of the previous Z and some parameters theta. And these can be quite complex. They're not typically convex problems. Of course, if you're solving a convex problem, this wouldn't be a big issue, but if it's non-convex, we don't know about the convergence of such procedures. They might require many iterations. There are parameters that require some ad hoc tuning, typically step sizes and so forth. And so the idea behind deep unfolding is to take this recursion that we use for iterative design and unroll it. So think of a recursion as kind of a circle. We unroll that circle and we make the steps of the iteration different stations along this linear processing line. And we pick a finite number, say L, of these iterations, and we just unroll them and lay them out in a linear fashion, where each point along this line represents an update of this parameter vector Z, of the vector Z that depends on, of course, these parameters theta as well. And so the idea of deep unfolding is to implement this linear unfolding of the algorithm, not using necessarily the steps that are involved in this recursion, but possibly using a neural network that has trainable parameters. And that's what I'll talk about. So these parameters theta, like the step sizes and other things we'll see, on which these iterations depend, become hyperparameters in the network. And then we use machine learning training to essentially fit these hyperparameters to achieve good performance. So the advantage of this approach is it retains the model-based structure because we're using this recursion here, which is based on physical signals, physical processes. But we're taking the advantage of machine learning aspect and allowing it to help us configure or tune this iterative procedure. And so it leads to networks that have fewer parameters than just black box models, because most of the structure in these iterations are known to us. There's signals or quantities that are known to us. And it has a relatively small number of parameters that we have to tune, which means we need less training, and it can be implemented much more efficiently. So in my talk today, I'm going to give two examples of some advanced transceiver designs or architectures. I say advanced because they go beyond just kind of the standard vanilla implementations, and show you how deep unfolding can be used to address such problems. So the first one will be in a MIMO precoder design, particularly hybrid analog-digital beamforming. And so that's the example we're going to look at first. So I don't know if you're familiar with this, but in hybrid analog-digital precoding, of course refers to the problem of taking symbols, S, and converting them into signals X, or in this case chi, that are actually going to be transmitted from the antenna. So S represents the symbols of data, chi represents the data or the signals that are actually transmitted from the antenna. So precoding is just the mapping between those two endpoints. And so in a hybrid analog digital precoder, instead of doing all of the precoding in the baseband and then having to have a different RF chain for every antenna, or in fact 2 RF chains for every antenna for real and imaginary parts, what you do is you split that precoder into 2 parts. A baseband part, FBB, that is much smaller in dimension so that you can reduce the number of analog chains that you have to build and implement. And then another network of RF phase shifters, referred to as FRF, that then take the output of these RF chains, multiply them by tunable phases, no gains, just tunable phases, before they're transmitted from the antennas. So the precoder design problems is basically how do you design this FRF, this RF network, and the baseband precoding network so that their product gives you the precoder that you want. And so a typical design procedure is to, first of all, design a precoder that you would design if you had an RF chain for every antenna and you designed everything in the digital baseband, and then try and find a factorization, FRF, RF precoder times baseband precoder, that gives you a good approximation of that I would say optimal design. Seems easy. It's a nonlinear problem, of course, because these are the factors we're trying to find here multiply each other. And there are some nonlinear constraints here that are basically there to guarantee that the precoding that's done in the RF domain is only based on a phase shift. So this is the difficult problem, nonlinear optimization problem, non-convex constraints. So of course this is going to require some kind of optimization procedure to solve it. We can also, of course, we vectorize the data into real and imaginary parts to turn it into more of a standard least squares problem here, where X represents the vector of coefficients in the RF precoder. B is a matrix that's a function only of the digital baseband precoder. So the conventional optimization procedure in this kind of problem is to alternate between solving for the digital baseband and the RF precoder. Solve for digital in terms of an RF precoder, and then solve for the RF precoder in terms of a given digital baseband solution. Now, the nice thing is that typically, for many applications, the baseband precoder, if you know what the RF design is, you can design the baseband precoder in closed form or almost closed form, and so that part of the problem is quite easy. The more difficult part is to find the RF precoder because of the constraints on the unit norm or unit amplitude constraints that result due to the use of phase shifters in the RF precoder. And so a very common approach is to say, okay, given a baseband precoder, how do I find X? Well, I do, say, a projected gradient descent algorithm where I just do gradient descent, and at every step I project back onto the unit amplitude constraints. Of course, there are variations of this. Riemannian manifold type approaches, of course, that could also be shown here for an example of deep unfolding, but I'm using a simple case here. So projected gradient descent, you just do basically a stepwise gradient descent using with a projection afterwards. This, of course, requires you to pick a step size. Maybe you could come up with an algorithm that would change the step size based on how the performance is going, how the convergence is going. But of course, there are no guarantees of convergence here to any global minimum. And there may be problems with convergence altogether. Well, what does a deep unfolding design do instead? Well, a deep unfolding design basically would replace this projected gradient update with a more general update of this form, where the next value of the RF precoder is a weighted combination of the previous one xl minus 1 and this vector w, or this vector u, which is a function of x as well, but also the digital baseband. So we separate it into two parts. And so this looks more like what you might find in a neural network type step. You have a set of weights, or you have a vector input, you have a set of weights, in this case 2 sets of weights, that process the data to generate the next output for this network. And then in this case, you might follow it at the end by some kind of nonlinear activation function to satisfy this unit gain constraint you have on the RF precoder. And so the tanh is maybe a good choice for that. And so here is basically what the network structure would look like for implementing the algorithm in this way. Again, this is a design algorithm, not really an implementation algorithm. This is something you'll be designing not offline, but perhaps concurrently while you're processing data through the network. A couple of things to point out here is this leads to a very sparsely connected approach because the weights are applied one-to-one on the data that enters the layers of the network. So each weight only affects the one element of X. So this is not a fully connected network in any sense, very sparsely connected network. But you can do batch training with a loss function. In this case, the loss function that we use is here. Basically just a weighted squared error difference between what we want to achieve, the precoder we want, and this combination hybrid approach precoder that we're using. Because it's a precoder design, it's independent of signal-noise ratio. That helps with generalizability. We don't have to worry about signal-noise ratio here. We just have to worry about channel. How does this? So we would train this particular device with a bunch of different channels that we hope are representative of the environment. But again, because there are relatively few parameters here, the amount of training that would have to be done is relatively small. So I'll just quickly show you some results here. This is, the left is spectral efficiency performance as a function of the number of transmit antennas. So hybrid beamforming designs are typically geared towards large antenna implementations where we try and reduce the number of RF chains. And on the right, we have the time complexity required to implement the design once training has already taken place. And that's where you see the big benefit. So you see on the right-hand side, once you have the network trained, generating the precoders is extremely cheap compared to the examples that are given here, some competing algorithms that are standard alternating optimization, projection gradient descent approaches that have been proposed in the literature. So you see a very, very large decrease in runtime. And in terms of performance, you don't see much loss relative to the blue curve, which would be the optimal design if you had full digital control of the network. And then the black one, which is the alternating optimization approach, but which requires significantly more computation, especially for very large arrays. So the big benefit here is by unrolling and turning it into a neural network that you can train, is you get the ability to tune the parameters of the network in a good way. But then once it's time to actually implement the algorithm in a system in real time, where things are changing at megahertz rates, the computation time is much, much less. And this is another plot that just shows, again, some performance curves versus SNR in this case, spectral efficiency for different numbers of antennas. And again, the performance of this unrolled network is very close to within a dB or so of what you could achieve with a digital precoder. All right, so that's one example. I'll give you the second example I'll give will be on the receiver side. And in this example, we're going to assume that we have a receiver that is connected, so the RF chains at the receiver are connected to low-resolution analog to digital converters. So this is one way to reduce the complexity and cost of large antenna receivers, is to try and reduce the cost and complexity of implementing the analog to digital conversion. One way to do that. So hybrid beamforming, of course, and hybrid receive beamforming could be used here as well. Here we choose to show an example for low resolution receivers. So we'll assume a setup with RF chains on every antenna in this case, but connected to low resolution ADCs, both the real and imaginary parts of each RF chain output, and those outputs would then go into a neural network based detector. We'll assume just a simple uniform scalar quantization scenario where the data h times x plus n is quantized by this function QB, this uniform scalar quantization. And there are two problems, of course, you can solve in this setting at the receiver. One would be you transmit some known training data, x, and you use that training data to estimate the channel h. So we vectorize the data and we write it in this way. There's a matrix P here that's a function of the training data, and that then is a linear function. Before quantization is a linear function of the channel. After quantization, of course, it's not. The problem, though, of course, is to estimate the channel h given the observations y for a known x. On the other hand, we can do the Kronecker product transformation in the different direction, and we can write this as the problem of detecting the transmitted signals x for a known channel h. So in this case, the matrix P is a little bit different, depends on the known h, and x is the unknown. What we'll see here is that this problem mathematically is essentially the same, right? They have very similar forms. The only difference, of course, is that the elements of the estimate h don't have any constraints, but the elements of x are constrained to be from a particular digital constellation. So let's look at the channel estimation problem first. So if you wanted to estimate the channel in this setup, this is a difficult problem because of the nonlinear ADCs. We're talking not just one bit, where the case is a little bit easier, but this could be 2 or 3 or more bits of precision. If you want to estimate the channel in an optimal, not machine learning way, but maximum likelihood here, ML stands for maximum likelihood, you could formulate the log likelihood function. It depends on the standard Gaussian CDF. It depends on the values of the quantization steps where the signal y is located. It's a fairly complicated optimization. Certainly it's non-convex. So once again, you'd be forced to do some kind of iterative procedure to try and solve this problem. If you go about trying to do that, many people have done this. What you find is that the gradient of this cost function is extremely ill-conditioned, especially at the tails of the Gaussian distribution, because, of course, the standard Gaussian CDF goes to 0 very quickly. And you run into numerical problems because as the values of S, again, these are the points on the quantization lattice. As you get higher, a little higher signal-to-noise ratio, the differences here become quite small, and so the gradient can blow up. It becomes very difficult to implement a gradient search technique for this particular setup. So one approach to doing this that we've used is to use a logistic approximation to the standard Gaussian CDF function. This is, the reference for that is again cut off at the bottom, I'm sorry. It's from a paper about 15 or 16 years ago. And this has slightly heavier tails that removes the issue with the ill conditioning. And it has this nice logistic function, which of course we see implemented in many neural networks already. And so it's a nice aspect of this. And then we just unfold the design. So instead of using the gradient as calculated here that's ill-conditioned, we use this modified gradient here. We unfold the estimation of the channel, the iterative estimation of the channel, and we end up with a structure like this. The trainable parameters in this case are indicated in red. So the step size becomes a trainable parameter, scaling becomes a trainable parameter, and in fact in this case, the matrix P, which kind of serves as a weighting matrix in this neural network and corresponds to the training signals that are used to estimate the channel, they also become trainable. So with this design, you can actually implement a system where you train to learn what are the best training signals to use to estimate the channel for a particular realization. If in fact you do that, there's a little catch here that, of course, since the training data goes through the nonlinear quantization step, you have to make that quantization a continuous function so that you can use backpropagation in order to estimate the parameters. This is a simple ReLU, I don't know, approximation to the quantization in order to help you do that. And here's some implementation examples. You can see on the left, for different numbers of bits at the ADCs at the receiver, you can see the unfolded performance is the red curve. The blue and black curves correspond to some classical techniques that have been developed based on the Busgang decomposition for nonlinear processes. You can see that the unfolding, because of that ability to have this extra flexibility and train these parameters, you can tune the network to have better performance. And again, implementation is trivial. Implementing the channel estimator is a very easy thing to do. And the other examples basically show the same thing, so I won't. But well, I will mention that the comparisons with the comparisons on the middle are with the standard iterative gradient descent method. You see we're getting better performance again because we're using tunable parameters from the network. And on the right, then, the benefit is in terms of, we're showing that there is some small benefit that you get if you actually train the pilots. We haven't found a lot of benefit in terms of performance in that sense, but at least in principle, that's something you could do with this network. And then finally, for data detection, the problem is basically the same. You just reverse the roles of the channel and the transmitted data. You get exactly the same model here. You get exactly the same problems that you would get if you tried to implement some kind of gradient-based solution. And so instead you use an approximation as we did before, and you end up with this kind of network structure for updating an estimate of the transmitted data on one end of a layer of this network to the value of this vector at the end of the layer. And they're training, again, it's chopped off at the bottom, but the alphas are trainable here. H is not, of course, trainable in this case. The weight matrix is fixed because that's the channel estimate. We don't have control over that. And then the final output layer, the psi function, is the function that we use to handle the nonlinearity due to the fact that we're assuming X is from a finite constellation. And so we make that a continuous function, and so that we can do backpropagation and estimate those parameters. And then you see here, in this case, we get quite a big performance improvement, especially at higher SNRs, compared with standard linearized methods that have been used for low-resolution ADC processing. Again, the reason for that is, first of all, because the BZF and BMMSE algorithms are not based on maximum likelihood, and second, because we have a tunable approach to implement this maximum likelihood receiver. Okay, so that's basically all in my talk. Deep unfolding, the idea again is to replace iterative optimization with a trainable neural network. It, in my view, offers a nice bridge between model-based and black box designs. At least I see a path to implementation, at least in 6G, that could use this kind of technique, a much more direct path than black box type models. I think it overcomes some of the limitations of these black box models, including it allows you to incorporate domain knowledge. The domain knowledge is built into these iterations because they depend on the structure of the problem you're trying to solve. You can retain this classical modular communications architecture, and so the parameters that you're dealing with are meaningful. The parameterizations are more concise, and so less training is needed, which I think is a critical factor at the physical layer where things change rapidly. And then, of course, it's easily customizable for different scenarios. And you know, as I said, deep unfolding is not a new topic. There are many applications beyond wireless. Sparse signal and image processing was one of the first. Image reconstruction, recognition, segmentation are also problems where this deep unfolding provides a lot of benefit. Radar optimization problems are starting to consider this deep unfolding type approach. Also, nonlinear, linear adaptive filtering, Kalman filtering is another kind of recursive type algorithm that depends on parameters you assume are known, typically, like covariances of process and measurement noise. You can envision a scenario where you try and estimate those along with the state with some parameterization, and they become, use some kind of tunable deep unfolding approach to do that. So it could generalize these adaptive filters that are used for many other applications. So that's all I have, and I'd be happy to answer any questions. Thank you. Yes, Monica.
Hi, thanks for the nice talk. So in the real world, we will not know the channel and the signals. So do we do the blind deep unfolding or we do recursively? What do you suggest?
That's a whole different problem. Now, of course, in communication systems, we typically assume we are training with known signals. That can typically be controlled. In most standards, there are known signals embedded into the standard that we can exploit for channel estimation. And so we can start at least with that. We can start with a standard algorithm and get an initial condition based on that. If you don't know the signals, if you're trying to, say, estimate a channel and do detection for a source that's non-cooperative, then yes, you would have to use some kind of blind approach. And again, typically they boil down to iterative optimization procedures that you could, presumably put into this framework as well.
Also, I want to ask something about the example that you gave where they used the blind box and the QPSK constellation. The decision reason was skewed. I mean, the decision reason was not same as the Gaussian thing.
Right.
But that may be because the noise that you have simulated may not be Gaussian.
Exactly, and that's exactly the point, right? Because you train for a particular SNR typically.
SNR and the noise, maybe the simulation that you have done. So, and it may not have worked in the real case because that noise is different from the noise that you have trained.
Exactly.
So if I go with that logic, so maybe neural network can appreciate more better if we kind of retrain again and again, maybe after a small block, we'll kind of understanding the channel better, and maybe the decoding is also in that sense be better.
Absolutely, that's exactly the approach you would use, especially at the physical layer where things change. They may be different than when you train the network, so you have to do retraining. But the problem is, because the channel is changing so quickly and the environment is changing so quickly, if you're using a black box model, the number of parameters you have to retrain in that scenario is very large. The advantage of this approach is that's much more smaller, manageable parameterization. So if you have to do that retraining on a rapid basis, you can get away with many, many fewer training samples in order to do that.
Okay, thank you.
Yeah, sir, one question here. Sir, here. So how about, sir, if I just want to know your comment over this. So rather than using these end-to-end learning structures, how about if we use learning structure only for the specific task and rest of this we keep our classical signal processing methods?
Yeah. And so that's kind of precisely what this is targeted for. You saw the picture that we were using here a minute ago. If I go back up here, we were just talking about designing the receive equalizer, the receive decoder, using this ML algorithm rather than the whole chain of the network. So yes, I think this unfolding approach is very well suited for retaining the modular design that we're used to, and just implementing the functions in each of these modules separately.
Thank you, sir.
So one question I have, so you mentioned somewhere that the unfolded version is faster than the regular iterative algorithm.
Not necessarily, no. No, if I said that, I was wrong.
Okay.
It was much more efficient than the standard iterative implementations.
Why is that?
Well, because the operations of the network are just simple multiplications. In other words, the amount of computation required to implement one layer of this network is much smaller than, it requires fewer steps than a typical implementation would. So
Okay, so
part
you're
of it's the
cutting down on the
convergence.
number of iterations.
Exactly. So because you're able to train these parameters and get better values for them, the convergence is much more quick. And so in L steps, you get good performance, which would take you maybe another factor of 10 more in a regular iteration. Yes, thank you.
But then you're losing, so if you're training more parameters, you're losing generalizability. So if you had to do this in real time, or if you
Right.
didn't have a lot of training data, you might worsen performance.
Well, but again, there's fewer parameters here than in a corresponding black box model.
Well, of course,
Yeah.
yeah. So, but compared to a regular iterative
Yeah,
model.
it's in between. It's the point here is that it's kind of an in-between approach. We try and retain all the advantages of the standard modular model, but you don't have to go all the way to a black box model, so you have some in between. So there's still a price to be paid for trading. There's still a price to be paid in that sense, but
Okay. I have more questions, but I'll not take away from my own talk.
okay, right. Sorry if I'm sorry if I cut into it. Yes.
Yeah, I just have a quick question, and that actually relates to the previous question. In a iterative optimization, one typically uses a convergence criterion, right, to determine the number of iterations. So effectively, translated to the unfolding, the number of layers is not fixed, right? Whereas here, you fix the number of layers. And the question is, how does one determine what the right number is, right? I mean, it could be, in a practical situation, you may have, one particular burst of signal where you require fewer iterations than another burst, right, in terms of reaching a convergence criterion. But now with the unfolding approach, you can only use one set of iteration stopping
Right.
criteria.
Yeah,
So is there a rational, principled way to choose the number of layers?
I would say, this is going to happen at training time. You're going to train the network for different values of this unfolding parameter L. And so ultimately will be a function of how good your training set is. So
I see.
If you have a sufficiently diverse training set that encounters these corner cases you're talking about, hopefully the value of L that you end up with will be sufficient for whatever you're going to find in your application. Now, of course, whether that's true or not is not known in advance, but that's you would do it at training time, basically.
But you may get, in practical situations, you may have the vast majority of signals, you require 3 iterations.
Exactly.
But then there are a few that you require 1,000, right?
Exactly.
And you're still making off pretty well, because on the average, that's a small number of iterations. Whereas here, you don't have that option, right? You have to stick with 3, you have to stick with 10 or
No,
whatever.
I fully
Yes.
agree with you. I think the only thing I would offer is the performance of this, which curve was it here? The one in the middle here where we implemented the standard gradient-based kind of optimization and we didn't use a fixed number of steps for it. We used, as you said, a threshold for convergence. So it was allowed to go on as long as it needed to for 3 different step sizes here. And you see that,
It
well,
still
at
is-
least for these cases,
Right. Yeah.
it worked out. But yeah, your point's well taken. It's certainly an issue. Yeah.
Great. Thanks.
Hi, yes.
Lee, 2 questions. One, in practice, the SNR is constantly changing. And you train at a certain SNR. Let's say you have a variation of 10 dB. Do this work? Have you ever tried this?
Yeah, so.
And the other is synchronization. You will leave, I assume, synchronization to the classical means?
You could. In principle, you could.
Or is it something that
You
would
could also
consider doing
implement
with
you could do unfolding for synchronization, right? Because it boils down to a gradient search out of a match filter or something output. So, but yes. Now in the first example, there was no signal noise ratio issue. The pre-coding design problem is independent of signal noise ratio. So there we don't have any issue. It's just channel dependent. On the receiver side, yes, it's going to be signal noise ratio dependent. So this is an issue, of course, with all machine learning algorithms. It's just a function. So the only thing I would say is it's going to be an issue here as it is an issue with any black box machine learning model. But the fact that the number of parameters are smaller means you can train with a broader set of the signal noise ratio or other conditions you're trying to mimic compared to a black box model, and hopefully become more robust to that. But you could still use whatever methods that are used for generalizability in standard black box models here as well. It's still ultimately a neural network. And so whatever techniques you use for generalizability in the standard case, you can apply here as well. So.
Thank you.
Yes, hi.
Hey, Al, thanks
Hi, Brian.
for a nice talk, Lee. My question is about the quantization. So you're adapting the quantization levels?
No, we're just using a uniform. We could. Now, again, everything's up for grab here. When you talk about a machine learning type implementation, this particular example used a uniform fixed quantizer.
Okay, but your training had to go back through that.
Yes, if
Yeah.
you're actually updating the training and trying to design the training data, and here training means training you use for channel estimation.
Yeah.
Since that training data goes through that quantization, and you want a differentiable, if you're doing back
Yeah.
propagation to design the network, you want a differentiable.
Yeah. I
function.
wonder how that would play in if you adapted those levels. Might. Yeah.
It
Yeah.
would certainly be an open problem, yeah. It would be an interesting problem. We haven't looked at that.
Thank you.
I've probably taken
okay.
more time than I was supposed to, but.
So if there is no other question, then let's thank Professor Swindlehurst again. The next speaker is Professor Namrata Bhaswani from Iowa State University, and she will talk about Byzantine resilient alternating gradient descent and minimization for partially decoupled federated low-rank matrix learning.
This is right from your Google Slides? Google Drive?
Yes, madam. But one thing, we have to make it full screen. तो नीचे का टास्क बार आ रहा है ना?
Oh, okay. Control L.
Control L we have done.
Oh, sharing में नहीं चलेगा.
नीचे का टास्क बार आ रहा है ना? Hello? Adobe Reader window. This is Adobe Reader window. So. इसको फुल स्क्रीन कर देना. वो नीचे का टास्क आ रहा है.
You probably need to close this, right? Control it. Okay. Hi, everyone. Can people hear me at the back? Okay. Thanks again to the organizers, Arpan and Monica and Kumar Vijay for inviting me. I'm very excited to be back. IIT Delhi is home. This is where I did my undergrad exactly 25 years ago. So I was happy to visit my department yesterday. And very glad to be giving a talk in this workshop and on campus. Okay, so I'll tell you guys a little bit about Byzantine resilient alternating gradient descent and minimization. This is based on these are three papers. And it's joint work with a lot of my current and former students. The work was started by Dr. Sayyede Sara Nayyar, who graduated in 2021. And it's joint work with three current students, Ankit, Ahmed, and Shilpa. And my collaborator, Dr. Sajan Lingala from University of Iowa, who works on MRI. So this is a longer talk. I don't think I'll cover everything, but yeah, I'll skip through some slides. Quick background on federated learning. So in federated learning, the idea is that you have multiple nodes, entities, or clients, whatever you want to use, that collaborate to solve a machine learning problem. The main point is different subsets of the data are available at different nodes, are acquired at the nodes and need to stay at the nodes because of privacy reasons and because of communication efficiency constraints. So each node, we consider the basic federated setting, the original traditional federated setting, where each node can only communicate with a central server or service provider that I call the center. The concerns, as I said, are communication efficiency, privacy, and then there is you want to be resilient to attacks by adversaries. Especially Byzantine attacks are one of the hardest ones to deal with. So all of these concerns imply one thing, that the raw data should not be shared with the center. Only the nodes can only share data summaries. We'll come to more on this in a few slides. Byzantine attack is a model update poisoning attack, where the attacking nodes know everything about all the other nodes. They know the algorithm, they know the parameters, and they know all the data as well. Different nodes can collude. And then the node output at each, the Byzantine output is designed in a way to maximally corrupt the final model that is learned, or in our case, the final low rank matrix that is learned. What a Byzantine node cannot do is modify the outputs of other Byzantine, non-Byzantine nodes, or delay communication. Okay. So here is, so I'll talk about low rank matrix recovery, or in machine learning language we call it low rank matrix learning. It's the same thing. So a low rank matrix is, you consider an n cross q matrix. Let's say I'm denoting it by x star with columns denoted by x star k, which has rank r that is much smaller than the matrix dimensions. And the goal is to recover or learn this from linear or entry-wise non-linear measurements of it. Low-rank matrices or tensors are everywhere. Traditional settings, a lot of image sequences with each image vectorized to form one column of the matrix are modeled as low-rank. Videos often are, background videos are modeled as low-rank. Product rating matrices, for instance, in product recommendation systems are often low-rank as a valid model. Modern ML, the state transition probability matrix used in reinforcement learning, I've seen work that models that as being low-rank and uses matrix completion to learn that. There is correlated regression models, which I'll talk about. And then there is the whole idea of low-rank adaptation, which is becoming very popular in model fine-tuning. The three main LR problems that have the most applications are matrix completion, which I'll touch upon. Low-rank column-wise sensing, which was a not so well-studied problem until 5 or 6 years ago. That's what most of this talk will focus on. It has the most applications, in fact, including, so multitask learning, dynamic MRI are the two most important ones. And then I'll briefly touch upon phase retrieval, which is actually a direct extension of column-wise sensing. And again, I'm assuming the federated setting where measurements of subsets of X star are, subsets of columns of X star are observed at the different nodes. So quick mathematical definitions. So LR matrix sensing was the first, essentially after compressed sensing, LR matrix sensing was like the compressed sensing equivalent for low rank matrices. This, I think, was created mostly to prove theorems. It doesn't have a lot of practical applications that I know of. Then there is matrix completion, which has a lot of useful applications, where the idea is you have a low rank matrix, but you don't know all its entries. You know only a subset of its entries, and you want to recover all the entries. Recommender systems, video are two key applications. So this is the extreme opposite. In low rank matrix sensing, you want to recover a matrix from global linear projections of the matrix. In completion, you have completely local measurements. So you need an incoherence assumption on the left and right singular vectors. I'll talk about that. And then there is the low rank column-wise matrix sensing, which is in between the two problems. Here you have linear projections of each column of the matrix. AK, and they're compressive projections. So AK is a broad matrix. It's an M cross N matrix with M smaller than N. And the goal is to recover extra. It's also an asymmetric problem. The first two are symmetric problems. And so then to solve this low rank column-wise sensing problem, we've introduced an algorithm that we call alternating gradient descent and minimization. Just to motivate that, there are, so if you consider an optimization problem, you want to minimize fz over z, there is two commonly studied optimization solutions. There is gradient descent, which is most popular because per iteration cost is the lowest, And when I say gradient descent, I include all versions of stochastic GD in it. But then for some problems, it converges very slowly because it needs a very small step size to work, or may not converge at all. Alternating minimization was designed, and it works only for certain types of problems where your unknown variable z can be split into two parts or two blocks, ZA and ZB, so that minimization with respect to ZA, keeping ZB fixed, is either closed form or otherwise reliably solved, and vice versa. But here what happens is the convergence is fast, but per iteration cost can be high because you're solving a full minimization over ZA, keeping ZB fixed, and over ZB, keeping ZA fixed. Oftentimes what happens is that at least one of the two minimizations of alternating minimizations is the slow one. The overall idea of all GD min is in one line, you replace the slow minimization by a gradient step, just do one gradient step. And this makes alt GD min both faster per iteration, and convergence is almost as fast as that of alt min. At the same time, what you buy is communication efficiency for federated or distributed settings. So that's the advantage. So let me introduce, so this was introduced for solving this column-wise sensing problem, which I'll talk about now. So here's the problem definition again. You have your low rank matrix X star, which is unknown. You have measurements Yk, which are Ak times X star k. Ak is known, and Aks are also assumed to be mutually independent across k. For the sake of proving guarantees, we assume AKs are random Gaussian matrices. For applications in MRI, AK will be a subset of the Fourier DFT matrix. So now my unknown matrix X is R, and let's suppose I know R, or I can estimate an upper bound on the rank R. I can factorize X as U times B, with U being N cross R. And B being R cross Q, so essentially it's your. So now my goal is to my modified goal becomes to solve this optimization problem right here. I want to recover U and B by solving this optimization problem. And in a federated setting, I have disjoint subsets of Yk at different nodes. So let's say I would have Y1 to Y10 at node 1, Y11 to Y20 at node 2, and so on and so forth. And same way, I would have the AKs also at the corresponding nodes. Key application is an MRI, where X star k is the vectorized kth image of an image sequence. In MRI, of course, we don't deal with the federated setting. We may be interested in distributed computing, though, for MRI. Okay, I guess the bottom part is getting cut off, but that's okay. So one assumption we need for this is the incoherence assumption, which essentially translates into saying that different columns of B star have roughly similar energy, or different images, the average intensity levels aren't too different across time, which is a reasonable assumption. I'll skip this. So now what does the algorithm do here? So I have defined my cost function f of u comma b. I start with a careful spectral initialization for u. This borrows from existing literature. There is one extra step that was needed for this problem. But after that, I alternate between a minimization step for B and a gradient step for U. Why? Because notice, if you look at this cost function carefully, U appears in all the Q terms. The summation goes, K goes from 1 to Q. Q is a large number. U appears in all the terms. So optimization with respect to U is the slow step. Keeping U fixed, if I wanted to recover B, notice BK, the kth column of B, appears in only the kth term. Right? So there's decoupling with respect to B. Which is why if I wanted to solve this problem where I want to minimize FUB over B, keeping U fixed, it decouples column-wise into this simple least squares problem. Here, dagger is the pseudo-inverse. which is very quick. So, and bk is each bk is an r length vector. R is my rank. R is something between 10 and 50, whereas n and q could be 10,000 or 100,000. So, it's a cheap least squares problem. The update for you instead of, we also, previous work, we had an alternating minimization algorithm for this problem, where the slow step was the update of u. That gets speeded up hugely because I'm only using one gradient update for u. And then I'm following it up with a QR step, which is orthonormalizing my output. Helps me set my step size easily, both in theory and in practice. And helps with, notice when I'm writing my x as u times b, there is a identifiability issue. I could always multiply u by a q and b, left multiply b by q inverse, and there will be a identifiability issue. So by fixing, by orthonormalizing one of them, I am taking care of the fact that I don't get one of u or b decaying constantly and the other increasing constantly in magnitude. So that's the Algy-Dimon algorithm. So the reference for this is Nair and Vaswani, the 2023 IT transactions paper. And then for initialization, you start with trying to do what standard low rank methods do, which is look at AK transpose YK is my estimate of the kth column of X. And it's not too hard to show, because if my AKs are random Gaussian matrices, it's not too hard to show that the expected value of this matrix equals X star. So in the limit of, if I have enough samples M, then each column would be a good approximation of X star. Except there is one problem. The summands are heavy-tailed. The summands are actually sub-exponential random variables with a sub-exponential norm that's too large. So intuitively, a few bad measurements can bias my average a lot. So the fix is to borrow the truncation idea from previous work. So I truncate, which is to say I sum over only the not too large YKIs. And that theoretically helps me convert my summands from sub-exponential to sub-Gaussian random variables, which are much easier to handle. And then I just wrote this in short form. I truncate each and I compute u in it as the top R singular vectors of this matrix X in it. So in short, this is my algorithm, complete algorithm. Okay. I'll let you guys look at it for a minute. Here is what we can prove about it. So assume the mu incoherence assumption of right singular vectors. And we set our step size, and step size doesn't have to be this fixed value. It could be any 0.4 could be replaced by any number less than about 0.9, and the algorithm would work. My number of iterations t is order log 1 over epsilon, where epsilon is my final desired error. So what my guarantee says is that if my number of samples m times q, so m is the number of samples per column and q is the number of columns. If m times q has the specified lower bound, the second assumption is basically kind of trivial, really. Then with high probability, within about log 1 over epsilon iterations, I will converge to within an epsilon of my true estimate. My u, which is my subspace estimate, the column span of X star is denoted by u star. I converge in subspace distance to u star to within epsilon. And each column is, I get normalized error of order epsilon for each k, right? And what this implies is, because of the gradient descent, so what our least square step has about the same complexity as one gradient update step. So the overall time complexity of the algorithm is only mqnr times log 1 over epsilon. Here I'm ignoring kappas. The communication complexity, if I were to implement this in a federated setting, I'm only having to exchange the gradients, is order nr per iteration, and then I have log epsilon iterations. And the sample complexity is, again, only a little worse than optimal. Only the initialization step needs a factor of r more than optimal. So, and compared with existing work, yeah, so this is what we have. The reason it's fast is because the decoupling, because of the decoupling. The reason communication cost is low is because the updates of B can be done locally at the nodes. I only have to exchange the gradients. All that the nodes have to do is each node shares its own partial gradient with the center. Center sums them up, implements a gradient step. Privacy is ensured. No node and the center, none of them can recover the entire matrix X star. BK stay local to the node. And then you can show that because you're doing this one minimization step, you are able to have an iteration complexity that is almost comparable to alternating minimization. And there is technical reasons for this. So if you're really familiar, this would make sense if you're familiar, if you work in the low rank recovery area. So the idea is estimates xk are decoupled given you. Okay. And then why is a new approach needed? First, because altmin is expensive, because update of U is expensive. Existing gradient descent based method, the factorized gradient descent based method, do not work because this is an asymmetric problem where you need a tight bound on the column wise error, which you do not get with either projected gradient descent or with factorized gradient descent, because in both cases what happens is my estimates xk are coupled across k. Here is a comparison of sample time and communication costs. Alt GDmin for this particular problem gives the best of all worlds. You get the best sample complexity, the best time complexity, and the best communication complexity as well. NR is the lowest you could go. Alternating minimization is not good for, and then you also get Byzantine resilience very easily using a modification of the same algorithm. Whereas in altmin, you would need to do a lot more iterations, which makes distributed implementations not very efficient. I'll skip the proof in the interest of time. So coming to designing Byzantine resilient solutions, Byzantine resilient gradient descent is a well-studied area. There's many estimators used, but the two most commonly used ones are geometric median, which is defined here. It's essentially a vector or matrix generalization of the scalar median. Cannot be computed exactly, but approximation algorithms exist. Except, and then there is the crumb estimator, which tries to find the z, which is for which the other ZLs are most closely clustered around it. There's a simple mathematical expression which is in the paper. Both of them work if at most less than 50% or just a little less than 50% of the nodes are corrupted. So it's pretty large. Recall, this was my alternating alt-GDmin algorithm, the basic one. Now to understand what we do for Byzantine resilience, we recall that what you have is a vertical federated setting. So you have subsets of yk are at different nodes. So what you do is, for the initialization, for a secure initialization, what you would do is you would, your node L, instead of what happens is the entire matrix X in it, column submatrices of X in it are available at my different nodes. So what node L will do is it will start by computing in the initial UL as the top r singular vectors of its own XL, X init L, and send it to the center. What the center will do is it will compute a robust geometric median based estimate of, or crumb based estimate, you could replace it by crumb also, of the U's as follows. Now ULs are subspace, are denoting the subspace, so they don't lie in a Euclidean space. You cannot compute the GM of ULs. But the corresponding projection matrix, UU transpose, does lie in a Euclidean space. Frobenius norm is a measure of subspace distance when you use UU transpose. So what you do is you compute the geometric median of these UU transpose, followed by finding the UL that is closest to this geometric median. And this is I call this a subspace median estimate, and this was, okay, this is our ICML paper where the reference for this. And then the center outputs ULGM and broadcasts it to the nodes. Now what this little piece does is the subspace median is actually, you could interpret it as Byzantine resilient PCA that can be used in various other problems as well. This helps us initialize well, and the rest of the algorithm, Byzantine resilient or GDMIN, essentially just consists of, you take your gradient step, take your gradients, instead of summing them at the center, you compute their geometric median or crumb estimator at the center, and then the rest of the algorithm remains the same. Right? And broadcast the new U plus to the nodes. Okay. So this is the main idea of the Byzantine resilient algorithm. What you can show about this is, again, under the same assumptions, you have the right singular vectors in coherence. You have at most, this should have been 0.4. So at no more than 40%, or really any number less than 50% can be used. And no more than 40% of the nodes are Byzantine. And you need, for the vertical federated setting that I'm talking about, you also need that the heterogeneity between the nodes, so my data is not homogeneous in this case, is bounded by a factor GB, which is small enough. Under these assumptions, and under basically the same sample complexity as the, or slightly worse sample complexity as the non-Byzantine case, you can prove the same results. So your estimate U star and your final estimate of X will converge to to the larger of, either it will converge to GB, which is the heterogeneity factor, or epsilon, whichever is larger. Right? So basically your error will decay exponentially until it reaches the heterogeneity factor, is what you can show. And in the interest of time, so let's see. So this was for one problem. For the next problem, I'll just keep it to one slide. Is there any quick questions before I move on? Ranjit? So kappa is the condition number of, not exactly X star of the, essentially, so the ratio of the first to the rth singular value, first singular value to the rth singular value of X star. So yeah, incoherence allows you to deal with some of the heterogeneity, but basically you still need a heterogeneity bound here, right? So B star L is my B star at my node L. The B stars from the different nodes should not be too different. If they are too different, then even at an intuitive level, you cannot tell if a node is being Byzantine or if the data is too different, right? So that's why you need a bound on, so all results for heterogeneous setting of secure algorithms for heterogeneous data will assume bounded heterogeneity. Here? No, this one also has kappa, same. You mean without the, so the attack free case, there's no problem at all. There you're just doing federated learning. If you don't need to deal with attacks, heterogeneity is not an issue. So that is a much more difficult type of heterogeneity. So when in low rank matrix recovery, the heterogeneity is coming from the fact, so there it's like partial heterogeneity, if I may use that word. The U star, the subspace is the same across. So the whole problem, the recovery of X star, you could interpret it as recovering basically the column span of X star, right? That is my global thing. So that does not have heterogeneity. So it's a much easier heterogeneous setting as compared to the traditional, say, classification problems, right? And the second thing, it's a set of problems or a fixed one problem, so you're able to prove much stronger results. You're able to prove geometric convergence. Right? Now, I'll take 5 minutes to mention this, that not just the LR column-wise sensing problem, but there's two other problems. There is the phase retrieval version of this problem, which actually we studied before this original problem, which also share this partial decoupling structure. So RGD min is useful for many more problems than just the first problem I talked about. So phase retrieval setting is instead of linear measurements, I have magnitude measurements of each column of AK extra k. Here absolute value means I have entry-wise absolute value. Then this becomes my cost function. Here again I have decoupling. U appears in all the terms, BK appears in only the kth term. In this case, if I fix U, then the update of BK is, instead of a least squares problem, it's a standard phase retrieval problem, except it's a low dimensional PR problem, which is again existing fast algorithms exist to solve it reliably. So your RGD min proceeds almost the same way, except here it's the min step is updating not just BK, it's updating BK and the phases or the signs if it's a real valued problem. So there's minor modifications. The initialization is different. Again, it's given in this paper. And the guarantees, as we know from phase retrieval literature, structured PR literature, are R times. So you need R, a factor of R more samples, both for initialization and for the iterations. Here again, RGD min is fastest and more communication efficient than Altman. Then there is the matrix completion problem, which is heavily studied. Last 15 years, there's been a lot of very nice work. Here, the only advantage of RGD min is communication efficiencies. Time-wise, it's because of here you have two-way decoupling. You fix B, oh, okay, this is a typo. This should have been a P, not a U, sorry. This P omega k is a projection onto the set of observed. So essentially, all it's saying is that not all entries of YK are observed. Oh, are we getting close to tea break? Okay, but the point I'm trying to emphasize is here you have two-way decoupling. This U should not have been a U. It's projection. It's essentially denoting that a subset of the entries are observed. Here again, the algorithm remains almost the same, except initialization needs extra steps. Analysis needs, you need to show incoherence of U at each step. So analysis needs more work, but a similar set of techniques. The advantage of RGD min here is only communication, not as much computation, because Altman is equally fast. And let's skip this. Yeah, Byzantine resilient design, again, for phase retrieval, it's almost the same as for column-wise sensing. They're pretty similar problems. For matrix completion, there is one extra step, which you need a filtering step to ensure incoherence of U at each iteration, which again, this is actually submitted work. So hopefully the paper appears soon, and you can see that. Guarantees similar to LRCS can be proved. One slide on alternating RGD min as a general algorithm. Excuse me, sorry, here, this slide, yeah, is what I needed. So RGD min is really useful for any partly decoupled problem, which means if you had your Z split as ZA and ZB, if there's decoupling over ZB, then you use minimization for ZB and gradient descent for ZA. And then there's many other problems which share this structure. Robust PCA is one example of a problem that shares this structure. There is tensor extensions of a lot of these problems also share this structure. And then there is partly discrete problems like unlabeled sensing and clustering, which again share the same structure, where RGD min could be hugely useful. Can I take 5 more minutes? Okay. So quick thing, what the other advantage of RGD min is it provides a very fast practical modification for dynamic MRI. I'll skip the details. Dynamic MRI can be interpreted as a LRCS problem. The practical algorithm needs 3 extra steps. You have a mean estimation step. You essentially consider, instead of a low rank model, you consider a 3-level hierarchical low rank model, with the first level being mean estimation, the second level being everything I talked about, and the third level being estimate the modeling error, because for practical data, you want the details in the image. For mean squared error, the first 2 steps are enough. For practical data, you want the third step as well, for visual performance. And then what we tried to do, and this is what motivated my questions for you, was we wanted to run experiments on 20 different data sets, different types of MRI imaging, brain, cardiac, vocal tract, 5 types of cardiac actually, free breathing as well as not free breathing ones, and a few others, different sampling patterns, all with the same set of algorithm parameters. And here, a simple algorithm like AltGDmin significantly outperforms even deep learning methods. The reason being, it's a lot more generalizable. And here, actually, we did try unfolding. My students spent a whole lot of time trying unfolding, and it did not beat the original AltGDmin at all. When compared, like if you were to compare 20 data sets, here I have 15, in our ongoing work we have 20-some data sets. Same set of parameters, you get the best of all worlds with a simple algorithm with few parameters. That's the main message. I can talk about details if anybody here works in MRI in the break. That's that. I'll end here, and I can take more questions.
Any question?
Yeah.
We like the median, right, as a means of robustness.
Sure.
And my question is, if the Byzantine attackers are colluding, can they not pull the median, right, in one direction or another? And do we have to assume that the Byzantine attackers are somehow, within the distribution? They're going out in the tails equally so that the median is close to the desired mean. Do you understand my question? If the Byzantine attackers, couldn't they pull the mean away, and such that the median would see a bias?
No, I'm not computing. I'm computing the median, not the mean.
Yes, that's what I'm saying. But
Yeah.
if the Byzantine attackers were to collude,
Yes, but there is less than half of them. That's the point.
but I'm saying if they all concentrate on one side of the distribution, can't they pull the median? Won't the median pull away to one side? Can't they create a bias?
They will pull the median away a little bit,
Yeah.
but not enough. So because you have you have just under 50% constraint, right?
Yeah.
So as long as you have sufficiently less than half, yes. So your estimates will not be as good as in the Byzantine free case. Absolutely.
Yeah. But there's no advantage to them collaborating? Could if the Byzantine,
So your errors will be larger, but not too much larger than the Byzantine free case, as long as your number of Byzantine nodes is not too large.
yeah. Thank you.
Other questions?
So in that case, let's thank Professor Vaswani again, and we have a tea break now outside. We will assemble again at 10:55. Just 10 minutes tea break.
Oh, and I should end by saying, if there is any students willing to look for graduate positions, I'm always looking for good grad students.
You have PDF or PPT?
Hey, how are you? Huh? I came yesterday afternoon.
Thank you.
Oh, good. Yeah.
Is another thing
Hey, give me
mistakenly
a minute.
the It was reserved for me for 1 day.
Okay, really?
I probably I asked for 3 and 4. I don't know.
So, but did you?
I asked them to continue, but they told me that I have to contact the company. Is it through you? Because I paid.
So can you book it yourself? See, we have money. We can reimburse you.
It doesn't matter, but is it the same rate? Not the same
No,
rate.
the rate will be higher. I can talk to you. I mean, actually, what happened is, if you remember, we actually circulated one form, and we said that we actually wanted check-in and check-out date or something. So how? Which nights? Which nights? No, not from your side. Actually, the mistake was from the hotel side. So we said that. So when we basically, if this person said that I will stay till fourth night, 4th April night, the hotel assumed that they will check out on 4th. If it is 4th April night, that means the person will check out on 5th. So they made a mistake, and we had to get it changed for many people. I think you didn't get back to us, or we assume that it's fine. So let me talk to Chandrasekhar. So right now your 2 night stay is not booked.
They told me that they will hold it for me, but they need to contact the company for payment.
No, I think you can just pay on your own. You will reimburse. That's why you send the bill, you reimburse.
So I will.
Monica. Yes. So he's actually the same mistake happened with him also. So his stay in the hotel tonight is not confirmed.
Okay.
So what I'm telling him is that let him book it on his own, and we will reimburse him later.
Yeah. Maybe we can go for the sea. We have a good kind of good snacks, maybe.
So I will write them an email, the same. Yes, okay. Thank you.
This is the last of before lunch. So we are, it's great to have Professor Joseph Safikan from Ben Gurion University. He's going to talk about analysis of overfitting and modeling error trade-off in learning systems using misclassified performance forms. Welcome.
Thank you, Afan, and thank you very much for the organizers organizing this event. I'm talking about overfitting and modeling error in the learning systems. This work was done together with my PhD student, Nadav Rosenthal. After a short introduction, I will talk about the problem of model selection in learning systems. The main problem is which model and which order we should use. And then I will present the misspecified camera bound that will serve as a criterion for optimization and for model selection. Then I will give two examples. One is on direction of arrival estimation in unknown clutter and interference, and the other one on linear regression. Consider the problem of estimating a deterministic parameter phi given an observation vector x, where we don't have prior knowledge on the true PDF. In these cases, what we usually do is trying to learn this PDF through some training sequence. We have some parameters phi t, phi sub t that are known, and the training sequence that are generated by the true probability density function. And then we use a parameterized PDF, a set of parameterized PDFs with parameters theta, theta m. M is the order or the index of the model. Using this training sequence and the true parameters, we actually can learn what are the values of these thetas. And then using these values of these thetas, we try to estimate the parameter that we wanted to specify through the data XP. So the question is, how should we set or what should be the model, for example, the architecture or the number of nodes in the learning problem? What is the model order? This is in supervised learning, and in unsupervised learning, we have the same problem that we don't know the true PDFs. And here we have the same block diagram, but we don't have the learning chain. We use only the data, and this data serves as data for learning these parameters. And here we consider a specific case of a problem where phi is a function of theta. We will see that there are many signal processing problems that in which we have this dependency. Phi depends on a set of parameters. And again, we ask the same question: what is the optimized or the best set of functions, and what should be the model order in order to minimize the mean squared error? So the mean squared error is given by this term, where this expectation is performed with respect to the true PDF, and phi is actually the estimator under the M model that we assume, and phi is the true parameter. So there is a known trade-off. Higher order models can cause overfitting, and we would like to minimize those fitting errors. And lower order model cause misspecification, where the model is not perfectly specified. A common approach for this problem is using model order selection methods, for example, minimum description length or a type information criterion, but they are not directly aimed at minimizing the mean squared error. Actually, underestimating model order typically results in higher mean squared error than overestimating. Because in overestimating, the main contribution to the error is the noise, and in higher signal-to-noise ratios, underestimation may cost a lot. We know that MDL in a low number of samples tends to underestimation, and it may result in large errors. There are other methods used based on cross-validation-based methods that they are mainly heuristic, and they require some tuning process we would like to avoid. I will give some examples where we encounter we encounter such learning problems. One is direction of arrival estimation in clutter. For example, consider this range Doppler map cell. We have a cell under test here, and we would like to learn the covariance matrix of the clutter or interference using neighboring cells, these blue neighboring cells. In fact, in this case, we have a target-free model in these blue cells, which is written here. This is the contribution of the clutter, and this is the contribution of noise. And here in the red cell, we have the target contribution and the clutter contribution plus some additive noise. We would like actually to estimate the direction of arrival 5. So this is a typical learning problem where we need to learn the covariance matrix of the interference. Another problem is deep neural networks, where we would like to learn the weights and the architecture of the model, and this model actually tries to mimic the true PDF, and the PDF used for this scheme can be written in this way, and we try to minimize this term, this norm, if the loss is mean squared error. So this is an example of supervised learning. And unsupervised learning, we have several cases. For example, parametric spectrum estimation, where we parameterize the spectrum with a set of parameters. For example, in this case, it's an autoregressive model. And instead of estimating the spectrum, we try to estimate some parameters of the autoregressive model here. And then the log spectrum is given here. We would like to minimize the mean squared error for this term and not for the parameters themselves. Another problem, by the way, here the phi is a function. Sorry, the spectrum is which is log spectrum, which is given by phi, is a function of these parameters. So this is exactly the second case of unsupervised learning that I mentioned. Another case is curve fitting and extrapolation. We have a curve. Here is the true curve, and we have some samples on this curve, which are these red stars. And we would like to do some estimation of the curve at a different point. So here we have a linear, because we can try to parameterize this curve by a polynomial and try to find the coefficients of this polynomial. So these are can serve as these coefficients, and we would like to estimate the value at this point, which is given here. Again, the phi, the parameter of interest, is a function of some hidden parameters. Again, we don't know the order of the model. So this is the problem. We would like to minimize some performance measure. This performance measure, in this case, we use performance bound. And these performance bounds need to take into account modeling error. Because if we have, for example, underestimation, then we have the modeling error problem. So, so we need a measure of performance, which in this case we will use it. We use misspecified parameter bound. So for the misspecified parameter bound, consider the problem that we assume some PDF. We have some unknown true PDF. This is the parameter of interest. It's the estimator of the parameter interest, and it can be shown that the maximum likelihood estimator asymptotically converges to a different value, not to phi. It converges to a parameter phi, which is given by the minimum Kolbe-Kleibler divergence between the true PDF and the set of assumed PDF. For perfect specification, of course, phi 0 is equal to phi. Okay. For this purpose, we need actually, if we talk about bound, parameter bound, for example, we need to define what is the class of estimator it refers to. So in this case, the MCRB is a bound for a class of estimators that are MS unbiased. MS unbiasedness in this case means that the expectation of the estimation error, but the estimation error should be equal to 0. But here, this is not the typical estimation error. This is estimation error with respect to the pseudo-true parameter, phi 0. It's not the true parameter. And as I said, the maximum likelihood estimator converges to this value, to phi 0. And this is the misspecified parameter bound. This is actually a bound that was proposed by Wong in 1986. But Chris Richmond and others brought it to the attention of the signal processing community since 2015, and the bound is given by this term, which is given by these two matrices A and B. This is the second order derivative of the log likelihood, and here this is the first order derivative of the log likelihood squared. In the case of perfectly specified problems, A and B are equal, and we obtain the regular parameter bound. And phi 0, as I said, is the truth that is given in this case. But and we would like to use this bound for as a criterion for model selection. The problem is that we have the dependency. We need to know what is the phi 0, because the bound itself depends on phi 0, and it needs to be known. Here we can see that phi 0 is given by this expectation. This expectation, log f, we know it because this is what we assume. But here, this expectation is taken with respect to the true parameter, but it can be performed using sample estimation. So the bound is given in this case for the two problems. And here we take into account the contribution of the bias. This is the bound on the covariance for estimation of phi 0, and this is the bias contribution. As I said, the maximum likelihood estimator converges to a different value, not to the true value. So this is the bound for the case of supervised learning, and for the case of unsupervised learning, it can be shown that this is the yes, please. Yes. Yes.
You have to solve the problem.
Yes.
The problem will become complex. You will not get a global value.
No, we don't have. We just perform simple maximum likelihood. We don't try to use some sophisticated methods for.
MCRB depends on the pseudo parameter. Most likely,
This is-
the problem.
Yes, but this is actually if you use sample estimation here, this is the simple maximum likelihood estimate. And I don't try to say that you have an efficient way to solve the maximum likelihood. This is the maximum likelihood estimator using the assumed PDF. Note that in many problems, you would like to, you cannot deal with the true PDF, even if you know.
It's okay.
Yes.
So, not in the limit is problem to pick up. I'm not talking about G.
Right, right, you're right. I'm not trying to say that it is a simple problem, but in many cases it is a simple problem, as I will show in some examples. But again, I'm trying to say, in some cases, the optimizing the true PDF, maximizing the true maximum likelihood, finding the true maximum likelihood is difficult. And then you try to change the PDF, use an alternative PDF in which the problem can be complex or much easier to optimize. Okay, and then you pay in model in modeling errors. Okay, so this is the bound. Again, as I said, we can find phi 0 using sample getting this problem. Yeah. Phi 0, as I said, it can be computed here using sample estimation. But there is a problem here that the bound still depends on the true value of phi, and I will show in two examples how we can deal with this problem. Now I will show two examples. One is direction of arrival estimation in clutter and interference. Assume that we have the data model. This is the target contribution. This is the clutter contribution and additive noise. And we have some training data. This is only the clutter contribution and additive noise. And the problem here is that we can assume that we don't know the covariance matrix of the clutter, and we can try just to estimate it. But in radar problems, the number of cells is small. We don't want to take many cells in order to make in order to estimate the covariance matrix. The reason why we don't want to take many cells is because if you go farther to cells that are far from the target location, the clutter statistics may change. So you don't want to get farther. So the number of training data is small, and in many cases the number of sensors is large. So just a simple estimation of the covariance matrix may result to some errors, and we may obtain very high errors. And of course, if we assume that this clutter occupies a small subspace, then we may have some underfitting problem. We don't model the covariance matrix accurately. So we need an accurate size of the clutter subspace, which is unknown. So this is the covariance matrix as I wrote here, and P is, as I said, there is the size of the clutter subspace. This is just simple sample covariance matrix, but by the way, in many cases, this matrix may be close to singular. And here we assume that we assume a given size of subspace of the clutter, and try to estimate the covariance matrix. In this case, actually, this is the classic estimation. The prior knowledge is that we know, if under the assumption that we have M, the clutter subspace is M, then the N minus M lowest eigenvalues are equal to the noise variance. So this is estimated in this way. And these lambdas are unknown, and then the matrix of eigenvectors is also assumed to be unknown, and they are obtained from the sample covariance matrix. So we reconstruct the sample covariance matrix, but this is some structure maximum likelihood estimate. By this estimation, actually, we can construct the PDF, the assumed PDF under the EMF model, and this is the estimator, simple estimator. And we would like to know what is the performance of this estimator. No. We would like to know what is the performance of this estimator that is given here. So this is the bound. In this case, we don't have the bias contribution. So the problem that I said that we need to know the true phi is not correct. Phi t here is this is the pseudo true parameter that we need to make it in account. So here we have the bound for different sides of the cluttered subspace, and we would like to minimize it with respect to n. So this is the result here, and this is the misspecified kernel bound, and this is our method, root mean squared error, for estimating the direction of arrival as a function of signal to noise ratio. For comparison, the MDL and AIC and the ACC provide worse results. Asymptotically, they converge to each other. The asymptotics, we don't have a problem of underestimation or overestimation. So in the asymptotic things are easy, but in the non-asymptotic region, it will perform better in this stage. As I didn't say that, but we have 12 training samples here and 11 sensors. The number of samples is very close to the number of sensors. Here we have 6 interference sources that are stronger than the target by 15 millimeters. This is the root MCRV as a function of the model order. And we can see that it looks in this way. In this case, the minimum is obtained at the correct value. What you can see here is that we pay much higher price, or the MCRV is much higher if we have underestimation, while when we have overestimation, the price is lower. But still, the minimum is obtained at the true value. Of course, in the low signal to noise ratio, we obtain that this part will be lower, or in other words, this part will be higher. So it will be more symmetric in low signal to noise ratio. But in high signal to noise ratio, this part will be sharp, and this part, the slope here, will be slight. Okay, this is another problem of linear regression. This is our data model, and the true data model with some order t, which is assumed to be unknown, and theta is the true parameter, which is also assumed to be unknown. And we would like to estimate the parameter phi, which is a different linear combination of the unknown parameter theta. We don't know the size of theta, but we know all the matrices H that can, all the transformation matrices that can translate theta to phi. So this is the, in the case of maximum likelihood, this is the maximum likelihood estimator, and this is the predictor. for 5. And in this case, we can compute the bound and we obtain this term. This is the contribution of the covariance, and this is the contribution of the bias, and this is some approximation. Here, what we did, as I said earlier, we need the true value of 5. We don't have the true value of 5. What we did here, this is actually the term that represents the bias contribution. So in order to assure that we have zero bias, zero true bias, we took the highest model order, and in this case, we don't suffer from high errors due to bias. Of course, there is an approximation because here we introduced some additional noise due to the fact that we considered higher model order. So here we obtain the contribution of the bias, and this is the contribution of the covariance. And we can see that this is very similar to what we know in model order selection in Gaussian problems. In Gaussian problems, we have this is the very similar to the minus of the log likelihood, and this is the penalty term. We can see that this is very similar to conventional model order selection, amazingly, but in this case, we know that we minimize the bound or approximated bound. Okay, this is the curve that we try to estimate its parameters. The red stars are the samples, and here we would like to estimate the sample, the measurement at this point. So this is we do it with some polynomial curve fitting, where these H's are the powers of time samples. And the extrapolation is very simple. Here is given linearly. And this is the root MCRB as a function of 1 over the noise variance. Here we can see the contribution, the MCRB at the true value. The true polynomial order is 8. And this is the MCRB at the true polynomial order. In case of overfitting, we obtain these two curves, which are higher. It's not surprising. In case of underfitting, actually, this is the contribution of bias. We do not reduce the mean squared error, the root mean squared error in this case. If we reduce the noise power. Something that is interesting is that at low signal to noise ratio or high noise power, we prefer lower model order than the true model order. This is due to the fact that we know the model order, or even if we know the model order, it is better to use a reduced model order because we are not able to estimate its parameters, the parameters of the polynomial. Okay, and this is the root mean squared error as a function of the number of samples in the training sequence, and this is the MCRB, our method, compared to the other conventional model order selection methods. The best curve here among conventional model order selection methods is AICC, but still it performs worse than the proposed method. Okay, to summarize, we presented a new model selection method based on MCRB. It minimizes the expected estimation MSE rather than decision error probability or other criteria. It was so it was based on the MCRV, which served as an optimization criterion, which takes into account the effect of overfitting and underfitting. And we applied it in two estimation problems. One was direction of arrival estimation, and another one was polynomial regression. We saw that the proposed method outperformed other existing methods for model orders. Thank you.
Theoretical categorization is the possible gap basically the titles of the bound. The bound is known to be tight asymptotically. This is proven, but here we use some approximations. And due to those approximations, we saw that it is not as close and a curve that we showed that it is not asymptotically tight. But this is something that needs to be done because of those approximations to understand what is the contribution of those approximations to the error. I think that's something that we have not done.
Very good talk, sir. To the extent I could understand it. So one question is, you showed how your proposed method outperforms the traditional convention methods. But how about the runtime and computational power needed?
I can show, at least in the example that we consider. Yes. For example, this term, this is not very difficult to compute. Usually we have here some constants, but in case of MDL, we have some constants that doesn't need some computation. But here, this is we already do this as part of the estimate. It's something that we already have. So the computation is not very difficult. In the other example, this is the bound, and we need to minimize it with respect for each model order. Doesn't seem to be very difficult to compute. So,
any other questions? Please,
thank you.
So we will have a poster session now upstairs. After that, we will have lunch break, and at 3:30 we will have the meet again for the session.